Recording.
Okay, good afternoon, uh, good evening to everybody. So now I have the pleasure to introduce Professor Felipe Linares. Felipe Linares is full professor in IMPA in Brazil, and today he's gonna talk about on the special properties of solution of Camassa-Holm equation and related models. So, Felipe, thank you very much for accepting our invitation, and you have the word.
Okay, thank you very much for the introduction. And this is a nice, a great pleasure to be here to commemorate this 100th session of this seminar. And then today I would like to talk about these special properties of solution of the Camassa-Holm equation and some related models. And so let me tell you about that. So we have the this equation here, what is called the B family. And the main purpose of this talk is to introduce a new unique continuation property for solution of this equation. So this work is a joint work with Christian Holm and Gustavo Ponce from the University of California, Santa Barbara. So the outline of my presentation is as follows. Is first part is a motivation. Then I will talk about the main results. And finally, I'm going to give the idea of basically, well, there are two main theorems, and I'm going to give most of the details of the first theorem. And the second theorem, yes, I'm going to give you some hint to follow the proof. All right. So we started with this uh, Camassa-Holm equation. That is the equation that is the most famous one in this B family. And it was first noted by Fuchs-Steiner and Focus in this work on hereditary symmetries. Then it was derived as a model for shallow water waves, right, by Camassa and Holm, and that's the name that this equation has. And the Camassa-Holm equation has received a lot of attention. There are many works related to Camassa-Holm. So I didn't cite specifically anyone because the list is very long. So I can mention, for instance, Constantin Molinet, Constantin McKean, Constantin Escher, uh, also Brezan, uh, who, who else that has a lot of work on that? Hal Holden, Gruner, Reinhard Jimenez, and many others. Okay, so this equation has a very interesting features. One is this is by Hamiltonian that is completely integrable model, right? And then you can see that as a if you take in this new equation, what is called the B family, with B equal to 3, so we would be equal to 2. Yes, B equal to 2. That becomes the Camassa-Holm equation, right? And then you can write it in an interesting new form. Instead to look at this equation here, we can look at this other equation, right? This one over here, you have b equal to 2. And if b is equal to 3, we can get a new one that is called the Gasperi-Processi equation, okay? So both equations, Camassa-Holm, the Gasperi-Processi, are by Hamiltonian and integrable models, right? And these are the only ones in this whole family, okay? So this family was introduced by Holm and Stanley. All right, so we keep going. Then we would like to talk a little bit about the local well-postness for this model for the whole family, but then we started with the local well-postness obtained for the Camassa-Holm equation. Okay, so we can have a result by Lee and Oliver and Rodriguez. And it said that if you started with initial data in HS S greater than 3.5, you will have local well-postness for the initial value problem associated to the Camassa-Holm equation. Okay, so you can also obtain, so you can basically apply the theory introduced by Lee Oliver. You can choose one of them, Lee Oliver or Rodriguez, and you can apply it to the B family. You can also use that if you want to study the initial periodic boundary value problem, right? And then you can have local well-postness for strong solutions. So you can have the following theorem. It said if you started with S greater than 3.5, right? So there exists a time that depends only on the data and a unique solution of the initial value problem associated to this family in that class, right? So you have U continuous in HS intersection C1 HS minus 1, right? And then you can also have the continuous dependence of the solutions from HS into the class of continuous functions in this Sobolev space. So you can apply the same techniques in order to prove local well-postness for the initial periodic boundary value problem too. Okay, so if we are now in the periodic case, we can have exactly similar results for the line. And then I had to mention that, well, you can wonder that S is 3.5, and probably with all these techniques and all of that, it may seem that you need a lot of regularity. And indeed, if you want to work in pure Sobolev spaces, you need to do that. And it was already proved that if S is less than 3.5, you cannot have well-postness. Okay, so this is the borderline, right? S equals 3.5. What I don't know is there is a result in the case S equal to 3.5. But if you are greater than that number, you get a strong solution for that. Okay, so, but then it comes up that the family, this B family, possesses Picon solutions. Okay, so these are solutions of this kind, right? And then you may like to think about the stability and all the stuff related to this kind of special solution, right? And for that, you would like to use, for instance, the local well-postness that I already mentioned. But one can observe that these guys here, they are not, these Picon solutions, they are not in any Sobolev space, not even from P different from 1, right? Different from 1 to infinity without including infinity, but it is in this space. Okay, so if you got one derivative and then you are in infinity, right? In an infinity, so you can have this guy in that space. Okay, so what is that space? The space of Lipschitz functions, right? And then the question is, can you prove some kind of local well-postness in that includes the class where this Picon is, right? So you can do it, right? And that was first done by the Lelis Kappeler, and Topolov in the periodic case, and the result was extended by Ponce and myself and Serderis for the initial value problem case on the whole line, right? And then we did it in the case of the Camassa-Holm equation, but then if you check the proof, right, either the Lelis, Kappeler, and Tobalov or Linares, Ponce, and Sideris, it can be applied for the whole family, or the whole B family, all right? And then I can say that there is a theory, right, by Constantine and Strauss about the stability of this kind of special solution they are called picans. All right, so we move, and then what is the explicit or the conditions to get some kind of local well-postness to include the pecan. So we started with initial data in H1, enter the Lipschitz space, and then we can prove that there exists a time, right, that depend on the norm of the initial data. This is a unique solution, right, of the whole family, so that the solution is here in H1 intersection L2 intersection L infinity with this condition here, right? And then we can have still we can prove that the map is locally continuous from this space X to this space Z, the whole CT of the whole time. But then we don't have local well-postness in the sense that I described before, right? So we just we have existing uniqueness, and then there is this condition on the initial data, right? That we only prove that this is locally continuous from X into this space. So we don't go from X to X, but we go from X to a different space, all right? So we don't have well-postness in the strong sense, all right? That makes the difference with the previous results. So I just say that if you started only in HS, so what you hope is to be in HS greater than 3. For the periodic case, we also have a result like that, right? So we started with the initial data in H1, enter the space of the Lipschitz functions, and then we can obtain existing solution, uniqueness, but still we have this, the application of the map from the initial data to the solution is locally continuous from X to CT. All right. And then there is many works. Also there is a long list of work in different contexts regarding existence and uniqueness for the Camassa-Holm, right? And in particular or in general for the B family. All right. Okay, so but today what I want to talk is about continuous dependence of solutions, right, for this B family. Okay, so the point is, so we have this family, the B family, and then we obtain, well, usually what in this situation for nonlinear wave, right? So what we want to know is the solution is in somewhere equal to 0. How can we say it about the whole set that contains the solution, right? So in general, we would like to say that this is equal to 0, right? And then what is the scenario here when we are talking about the B family or the Camassa-Holm equation? So the first result, it was obtained in that direction by Ponce and myself. And then there is a slight improvement by Holm and Ponce. And we started with B. So we defined the B for anyone, but I think the interesting cases are B between 0 and 3. And then if we have this condition, let me see that I have something that you can see it. All right. So we have a solution of the initial value problem for the B family, B between 0 and 3, in the class described in the last theorem. Okay, so you started with initial data in H1 inter the Lipschitz class, right? Then we have a solution there, right? And for there, we can say something. If there exists a time t naught in the interval minus t, alpha and beta in R, alpha less than beta, with this equal to 0, right? And the derivative at the time t0 is not strictly decreasing, right? Then the solution is identically equal to 0, right? So this is a kind of unique continuation principle, right? Okay, so, and this is, we have to be very careful with this situation about the result is totally local, right? And then because you can be around the conditions to have a blow up for the Camassa-Holm, for instance, but then we, with this hypothesis, we just look it around some point locally, right? So this is the case when you are on the line, right? So what can we say about the case where we are considering the initial periodic boundary value problem? Let's see what happened in that case. So we have exactly the same situation, right? So you started with the same local solution that we started, that we proved without well-posedness in the strong sense, right? So, but then we can, in these results, we also include the Picon solutions. And then if there exists a time t naught in this interval minus tt, alpha in 0, 1, right, in the torus, so that this is equal to 0 in this interval, with this derivative t naught not strictly decreasing, then we can conclude that the solution is identically equal to 0. All right? And so this is quite different from the result that you can obtain, for instance, in the case of dispersive, nonlinear dispersive equation. All right, so let's move to say some comments. Okay, so the hypothesis that we give in the previous slides, I said, like this one here. Okay, so this is, everything is nice. So we have this condition here. Then we can say that this derivative is well defined pointwise, right? The first thing. Then if you want to have some result like this for the KDB equation, you can know it, right? You don't have a result like that for KDB equation. But you can go and try to solve, to use Soa and Chever, and then you can obtain such a result, right? So in particular, you have a difference of two solutions, right? So you can also apply the theory of Sot and Chever, and then obtain the unique continuation, right? So what is the condition there? It is like, so you have a solution of the KdV equation, right, in a open interval, right? Then you can have the solution equal to zero in the whole strip, okay? Contain the open where the solution is equal to zero, okay? Then you can do this, as I mentioned in this remark, you make the difference of these two solutions, and then you can obtain things, right? But then for the Camassa-Holm, right, we can assume that U2 is equal to zero, all right? So we have a result only in that case, right? So yeah, difference, we don't. Okay, and one interesting point here is that with this condition that we have, so for the Camassa-Holm, right? So Camassa-Holm of the B family, so we are saying that it is just vanish in some interval, right? With this condition of the derivative, then we have unique continuation, right? But then if we look at the Benjamin-Ono equation, right? Or the Benjamin-Bonnet-Mahoney equations, they share exactly the same property, right? And what is common between these three models are that they are non-local models. Okay, so it's different from the case of KdV equation. Okay, so for Benjamin-Ono equation, Benjamin-Bonnet-Mahoney, and Camassa-Holm of the B family, the results are in the same way, right? And it was mentioned, but this is a delicate point, right? It said that, so when you say it, okay, you can have a different unique continuation principle, but then this leads to, if you don't have this, you may lead to blow up for solutions of the Camassa-Holm equation, for instance, right? But then, so our result is no in that direction. We are doing different things. We don't touch the sign of the derivative, right? That is important when you are talking about a blow up for the Camassa-Holm, for instance. Okay? So everything is log. All right. So what about in the periodic case, right? So let me see. You have in the periodic case again. You started. Okay. So this is. All right. So what is the? Let me see. Yes, we have something here. Let's see. Okay. All right. Mhm. Okay. So what happens? So can you say something better than what we did before? This is a very interesting question, right? So what happens if you started with as a constant, right? So the solution has to be, if there is a solution, right, different from that, it should be identically equal to zero somehow. Okay, so what I say is given C naught in R, taking zero from that, alpha and beta in R, so there exists an initial data, making this possible in a small interval, right? In an interval, alpha beta is not necessarily small, such that the corresponding solution satisfies this. Okay, so we can find initial data satisfying this, right? and then the corresponding solution satisfies that condition. So, in particular, the solution is different from C naught, right, for all t in minus t. Okay? So we can compare with the previous one, right? So in this case, so we have initial data. No, we started with the solution, this cancel in a interval alpha and beta. So you have the derivative with this condition is not strictly decreasing, then you have u identically equal to 0, right? And for this one, so we have this initial data that is like this initially, right? Then you have the derivative equal to 0, okay? And the solution should be different from a constant, okay? Otherwise, it's going to be 0 everywhere. So you can say exactly the same if you look at in the periodic case, right? So you can find see if the initial data if the constant is different from 0, right? Then you may find a solution different from 0, right? Okay. Otherwise, it's going to be equal to 0 with these conditions over here. Okay. So this is much better than what we said before. All right. So this is if you started with this equal to 0 in some place, then we have unique continuation. The solution is identically equal to 0. Otherwise, you may have the solution different from 0. All right. Okay, so how can we prove such a result, right? So what we need is to find, right? So the initial data, right, that is equal to C naught in this interval alpha and beta, and then to construct this initial data with that condition in order to make a solution different from 0, right? So you may have an extension of the solution, right, that is different from 0 whenever C naught is different from 0. Okay, so we can do that explicitly in the case of the real line. For the periodic case, well, we can start it exactly in the same way, right? Try to find explicit form or explicit uh, initial data, but in one point we need to use the implicit function theorem, right? So but even in the previous case of the unique continuation, we explode the properties of this operator over here, right? So we have this operator, this is a non-local operator, and then we can have explicit solution, explicit form of the solution, okay? And from there, we can construct the initial data that we need with the conditions that we are given in the theorem, right? Okay, so what I'm going to do now is try to explain, there are some basic steps there, okay, basic mathematics in the steps, but I think it's interesting to see how can we construct something for a nonlinear equation, right, explicitly. Okay, so if we look at the equation that we are working with, so we have this expression, right? So the derivative in t at one in time equal to 0 has to be 0, right? And then the nonlinear part is given by this before, and we are going to give like a proof in the case 0, 3, and then when b is equal to 3, right? So we are announcing already that if b is equal to 3, so there is less difficulty, right? Because this derivative in w is not going to appear. Okay, so let's start to work in this set, in this interval 0, 3. Okay, so we have f, this is the nonlinear part, and then we can write explicitly this operator. Okay, so we have this operator, the derivative, the one minus the second derivative, the inverse of that, is given explicitly by this formula. It's just the convolution of the sine times the exponential, right? Convolution with g. Okay? So explicitly, this is the form that we have in the equation. All right. So what we try to do is, well, we started here in this interval alpha and beta, and then we want to have for the initial data between alpha and beta equal to a constant, right? And then from beta on and alpha before, we need to satisfy some conditions. So we hope to, we wish to have a solution that is smooth, right? And then has some so compact support somewhere, right? So we do the computation, we plug in there the function that we are looking for. So initially it has to satisfy these conditions, right? And then what we need to find are these two expressions, right? Or these two numbers, AB and BB. All right. So this is very elementary. So we go for to see if we can have the expression that we want. Okay, so if we started with an extension of the initial data that is say infinity with compact support, right? With a we have to give some conditions before alpha and after alpha and after beta. So we need from minus infinity to alpha to satisfy this condition because we already know that initially u naught it should be equal to c naught, right? And then from beta and on, we need to satisfy the other condition that's just come from the explicit form of the equation, right? So we have this form over here, minus beta minus epsilon, right? And then we get these two conditions to satisfy, right? And so what we want to do is to find the extension. All right. So as I said before, we have these conditions, and then for the nonlinear part, we need to satisfy this, and then also when they touch in C naught, we got exactly these two values, right? But then if you started like that, you are not in the condition that you would like, right? Because it's just a constant. And then you need to have initial data, say infinity with compact support, right? So what we want to do is, well, we concentrate either on beta to infinity or from minus infinity to alpha, right? And the proof is going to work in if for beta to infinity is going to is very similar to the case minus infinity to 1. All right. So we have to start with a first approximation. Okay, so we started with this function that satisfies the condition that we want, but this function is just a electric function, right? And we are asking for a same infinity function with compact support. So we have a electric function and we have also compact support, right? And so we want to start with this to construct a smooth solution. Okay, so we can check right away that we are in the right conditions, right? So we have this W naught have to satisfy this condition here and also satisfy the other conditioning for W0, right? And then what we got is this. In some point, we need to have 0, right? In that interval. And okay, this is just this equal to 0. We got the condition in the other interval. When we hit this interval, we will be 0, right? This is going to be 0 everywhere, but then this is just in the point beta. Then we can choose this in this form, right? And then what we have is basically this integral plus something, and that something is given by this integral evaluated in C naught. All right? So we are okay with the condition that we want to have for the initial data. Okay, but still, this is no smooth. To make it smooth, we do the trick of, we know already that this is just take a function that is infinity with support, so compact support, even or negative, with the support in the right place, right? The integral equal to 1, and we define these approximations like that, okay? And then we have a nice function that is now say infinity with compact support. All right, so but then we need to check that this is going to satisfy the condition that we need. All right? And this is what we do next. So we have this approximation, this is infinity with compact support, and then the values for any epsilon positive in this region and also in the other region. This is equal to 0 if we are in the interval alpha and beta, right? And then this integral is going to be 0 when epsilon is going to 0, tends to 0. All right? So in the integral from beta to infinity, we are going to have this number that we already obtained, right? For the Lipschitz with a compact support function that we construct first. And then we check that, in fact, it satisfies the condition that we are giving in the intervals, right? When you take epsilon to 0, right? So you satisfy what you want for the for the construction that we already have, okay? It satisfies for any of these approximate solutions. Okay, but then we have, still we don't finish with that. It gives us an approximation. And then what we want to do is now make a perturbation using this function that we already obtained, right? So for some epsilon, we have all the properties, and then we have to perturb this just to complete the argument. So this is the difference when you go to the case of the periodic boundary value problem, because we don't know explicitly how to deal with this perturbation. Okay, so this is next. This is next. Okay, so we have to ask for the conditions in order to obtain some value of lambda that makes the initial data that we want to be realized. Okay, so we have all the conditions here in W epsilon naught, and then you have a perturbation of that. Okay, and then you see that we got a restriction before when we constructed this function here, right? So you can see that gamma had to be this number in order to get this nice approximation, the first nice approximation. Then we have to look at the case when b is equal to 3, right? But then for b equal to 3, we don't have to deal with the derivative of the initial data, right? And then we can start with something that is as before, and then we just perturb this initial data, okay? And it had to satisfy the condition that we mentioned before in order to get the solution, all right? So B3 in for the initial data that we have constructed satisfies all the conditions, all right? So this gives the proof in the case of the interval beta infinity, and then as I mentioned before, minus infinity to alpha is going to be similar. For the, okay, so this is basically, it's exactly the same as we did before, and then we finish the proof on that. And if you want, this is doing backwards, this is software, okay, one more. So for the initial value problem, for the boundary value problem, so again, we use explicitly the form of the solution, right? So of what the solution that we wish, all right? But then this kernel is a little bit more complicated, and in some point we need to complete the argument by using the implicit function theorem, right? So that would give you the final result in that case. So I think this is all for today. Thank you very much for your attention.
Thank you very much, Felipe, for your very nice talk. So now we have the turn for question comments. So if anyone has a question or comment, please just do it.
Felipe?
Uh-huh.
Is
Yes.
Carlos.
Uh-huh.
A curiosity, thank you very much for your excellent lecture. B is a constant between 0 and 3.
Uh-huh.
When B is bigger than 3, it's possible.
I think so, but the point is that between 0 and 3, they have this physical meaning, right? So you can have the equation for any B positive, but meaningful models appear between 0 and 3.
Okay, it can be negative.
I don't think so.
Okay.
Yeah, because after you get the equation, it seems like, okay, you can take any B, right? But if you want to follow the modeling, right, to make this physical, make some sense of that, I think you have to restrict it to be between 0 and 3. Okay. But yeah.
Okay. Thank you, Felipe.
Okay, thank you.
Felipe, I have also, also in your proof, we need you need no that b should be positive and less than 3, no, because you have gamma, the number gamma, which is the square root of b divided by b minus 3, no. So
Right. Uh-huh.
uh,
Yeah, but this is a technical
yeah,
a technical issue, right? Because by the construction.
yeah,
Yes.
okay,
So so if you have b is smaller than 3, okay, so you can do this approximation, and then you get the things explicitly.
yeah,
If b is equal to 3, you may, in this case, it's very simple, right? Okay, so you don't have to go to the whole way I went, because you don't have derivative there in the nonlinear part. Okay.
and b equal to 0.
I don't know. This is it can be difficult, right? Be equal to 0.
Okay. I have another question. Is that you have considered the case where you are in the line, right, and also in a period domain, right?
Yes.
Is it possible to deduce a similar result in the half line, for instance, when you have just one boundary condition in one side? For this kind of, this kind of unicontinuation property.
No, I haven't seen, no, even in other situations, like for instance, in the first theorem I mentioned that we proved before, like you have a small interval where it's equal to 0 with the derivative that is not decaying, right?
Yeah.
So I don't know if there is something that we can say that you are with some boundary value problem in one side and then free in the other side. I don't know. I haven't seen any result like that.
Okay.
But it's a good question, yes.
Yes, and for instance, your strategy here to this let's say negative result, I do not see, but maybe you can. Is it important that you are in the half line, or you could make some similar construction?
No, the point,
From the convolution, right? So
Diego, is that you are using explicitly the operator, right? And then you can define it in the whole line, right? Or in the torus.
Yeah. Okay.
Right? If you are half line, so you have to came up with how to define this operator, right? Okay, this is the 1 minus the derivative square. Okay, so can you define this operator, the inverse of that, in the half line? To start with, right? You want to follow this proof.
I have some explicit formula in the case of the integral formula in the case of this operating bounded domain. Okay, I can maybe if I find, I can send you to.
Okay, thank you. Yes, yeah, because it's the main point is this, right? We have the solution explicitly given.
Yeah.
By this convolution, right? This operator that is has a explicit form with the convol with some function there. Yeah.
Okay. Okay. So thank you. Is there any other question or comment? If not, thank you again, Felipe, for your very nice talk.
Okay. Thank you.